guys. Good to be in Toronto. It's my first time here in many years. I think I was here when I was 10. Felt like I was going to fall through the glass floor of the CN Tower. It was a riveting experience, I think is what it was described as. So I'm here today. I'm from Google. My name is Yufeng, as Mark mentioned. I'm a developer advocate. And that means I come out and I talk to you guys, but I also then kind of bring that back into Google. I work with the engineering and product teams to try to make our products better. And I love chatting with the community and hearing about all the awesome things you guys are doing, all the cool things you're building, as well as all your frustrations and feedback that you have about stuff in general. You know, what is cool that you guys are doing today? What interesting things have you come across? You can find me up on Twitter at YufengG. And yeah, with that, let's get started. Like Mark said, time is of the essence. So I'm also a runner. I like to cook, and I like to build things. Hardware, software, sometimes both at the same time. And in the theme of today's presentation, perhaps learner of machines. So this is our roadmap for today. I will not show this roadmap again. So if you want to memorize it, now is your chance to do so. Basically, we're going to talk about three kind of big ways and some bonus material at the end. And then we'll wrap it up. So first, I want to talk about just overview of machine learning. Everyone's talking about machine learning. I think at this point, we can safely say that just about everybody in this room has at least seen or heard the word machine learning, if only just from their program this morning. So what is machine learning, right? Everybody wants to do it. Everybody wants to get in it. And the kind of short answer to that is just machine learning is learning from examples and using that learning to answer questions, right? We're not just learning for the sake of learning. We want to make useful predictions, shall we say. And so answering questions is the key. We have a problem that we want to solve. And in this example, right, is differentiating perhaps an image between a cat or a dog. And I like this image because it has a lot of cheese on it, right? Lots of layers of Swiss cheese. And it's an example of what these quote-unquote deep neural networks are doing. And that's kind of like a hot term these days. And basically, if you look at the bottom layer, right, your biggest slice of Swiss cheese, all the data is coming in, and it's going through these neurons. It's meant to model after the brain, after the synapses in your brain. And as each pixel, each of these holes in the Swiss cheese are analogous to pixels. And they basically just go through a multiplier. Each dot is a multiplier, times 0.7, times 0.9. And if that multiplication yields a value above a certain threshold, and that threshold is the key, that's the learned value, then it moves on, that value moves on to the next layer of Swiss cheese. And this happens a bunch, right? And eventually, you get to an output layer. And then, depending on which one it lands on, it's either a cat or a dog. And these thresholds, as well as these multipliers, are what is learned by the machine through training. And basically, when neural networks were first introduced, there were two layers, the bottom layer and the top layer. And then they decided to add more cheese, because adding more cheese is always a good thing. And so then they ended up with deep neural networks. They like their fancy terms. So if my clicker works, back in the day, in the 1950s, machine learning scientists and computer engineers, this was all worked out. They had neural networks. They were modeling synapses, and it was great. They figured all this stuff out already, but they didn't know if they were right, because there was not enough of data, processing power, and networking speeds to like pull it all together. And so they didn't know if what they were doing was really on the right track or not. They said, you know, this looks good, we're getting some good preliminary results, and that was pretty much it. But of course, in the intervening 60-odd years, we have now gotten a lot of these checkboxes. And in recent years, we've really seen this resurgence of machine learning, perhaps an explosion. Maybe that's too soon for Samsung. But we've gotten the data, right? We have data, we have processing, we have network. Specifically, we have massive data centers warehousing your big data or your just lots of data in general. And we have processing power in the form, thanks to the video game industry really, of GPUs, right? Graphical processing units allowing massively parallel computations. Remember the Swiss cheese? All those pixels need to get processed in one push, and that's exactly what GPU is great for. It renders each frame of your screen one screen at a time rather than one pixel at a time and just kind of working in serial. And of course, networking. We now have incredible networks because chips work at the nanosecond scale. So you need networks that need to work at no slower than, say, the microsecond scale. So advancements in networking allow us to tie together lots and lots of processing power to make data centers, or what we perhaps used to call supercomputers. And so thinking about the data center as a supercomputer, data center as a supercomputer, supercomputer as a data center. But basically, you have now, because of advancements in the infrastructure side of things, access to all of this, and that's fantastic. So at Google, we've seen a huge growth of machine learning internally. Over the past few years, these are basically directories with machine learning models, and then the number of those machine learning models contained in the Google code base. And so, we've seen that just skyrocket. Specifically, some Android apps that you guys hopefully know and love. I'm not going to go into each and every single one of these in the interest of time, but hopefully some of these you recognize. And hopefully some of these you can think of how they're using machine learning, because a lot of times there's this question of, oh, machine learning is really good. It seems to be useful, but how do I use it in my app? My app does not do image recognition. I'm not collecting pictures. My app also, it doesn't record any sound or do any language processing. But a lot of these apps also don't take pictures. They don't have you speak into them or sing into them and try to recognize what song you're singing or anything like that, right? A lot of these are still yielding useful and vastly improved user experiences through the power of machine learning. So let's move on to the kind of main points here. But before we do, I want to touch on this kind of training versus prediction thing. Machine learning, as we said before, is learning through example, right? Showing examples to give predictions. And these two operations, if you will, are somewhat distinct. They can be meshed together, but for our purposes, we'll say they're distinct. And there's a distinct training phase and then a prediction phase. The training phase, generally and hopefully, is much shorter on the grand scheme of things in time than the prediction phase, in that you will be predicting for a lot longer and for a lot more requests and a lot more processing power than in training, right? Everyone's focused on training, and rightly so, in that those improvements yield and show themselves in the prediction phase, right? When you're actually doing useful things, categorizing images or predicting what your reply to an email message should be. But the training side of it needs powerful parallel computations, whereas the prediction side perhaps doesn't need necessarily as much. And there are other considerations beyond just the power of the server, such as latency, flexibility of deployment, and things like that. And so this is one way to kind of think about the areas of machine learning that you can do for the prediction side of things, right? Because training is going to happen on the server. You're going to need lots of horsepower, you're going to need lots of data, lots of network, and you just got to crunch those numbers. And that's going to happen mostly on the server, because anywhere else is going to be limited in at least one of those areas, whether it's because your phone, you're trying to do machine learning on your phone, because your chips, yeah, we have really powerful computers on our phones today, but it's still, of course, no match for hundreds of processors networked together in a data center. So local is referring to on your phone. Cloud is on the server. And then pre-trained and custom is referring to whether the model is coming to you already trained. It's already ready. All the training has been done for you so that you can just go off and do the prediction. And then custom is where you're doing your own custom training and thus custom predictions. You have a custom problem, and this is, of course, the question that often comes up when talking about machine learning kind of APIs or any simplification is like, well, my problem is special. I have a very particular use case. I need to categorize PVC pipes, the bendy ones from the straight ones. Do you have an API for that? And it's like, well, not really, but you could build your own. So let's jump over and see. I built a very simple app. I didn't want to, like Mark said, mobile is everywhere now. So I can't really compete with the design chops of everybody. But I built something real simple here. Let me see if I can get this to show up. So I'm using a interesting hack to show my screen. So basically what we got here is, oh, this microphone's in the way. Okay. It's, there's literally text, a drop-down, and 2 buttons. The text reads, use the floating action button to select an image. So I'm going to click down here and pick myself an image. It's going to show up here, and then I can call one of these 3 things that we're going to kind of talk about. And that's the whole app, right? So as an example, if I go ahead and click the floating action button, and I go to the gallery, and of course, the first set of images is a bunch of screenshots. Let's say I pull up this picture of my keyboard, right? So that's what it looks like. And then I would press call, and it would call one of these APIs, and that would be great. So I also put some screenshots up here in case this didn't work. So there's that, picking, choosing a picture, and in this case, I put a wheel there because there's lots of wheels in Toronto, it turns out. And so the first piece of our little quadrant pie that we're gonna fill out, don't worry, is called the Android Mobile Vision API. Perhaps some of you have heard of it. Any takers? Anybody played around with this? Nothing? We got one. All right, two. So the Mobile Vision API is really 3 APIs. It does barcode scanning, your usual QR code, barcode stuff. It does text, your optical character recognition, taking a picture, turning it into letters. And then it does face detection, not face recognition, face detection. So detecting a face, not saying face A and B are the same. We're going to focus on the last one because the first 2 are, well, less interesting, potentially. Face detection is a challenging problem for a number of reasons. The main one that comes to mind is that the generic face, how do you define the generic face, right? If you were to write a program that takes input a picture and outputs, is there a face in the picture? Doing so with custom code and logic and tons of if statements and for loops would be really, really hard. You probably need else statements too. But with the Mobile Vision API, it's literally built into Android. You don't need to pay the monies. You don't need to use the network. It's all local. So naturally, it falls under this category. You don't need to worry about training a system with lots and lots of faces. And you don't need to call anything in the cloud or set up a server. It's all Java code, and it's all right there in Android Studio. So let's see that in action. Of course, the picture that I had from earlier is, it's not going to do. There's no faces here. So what I've set up is it'll take the response, and all it's doing is putting a box around the face, and the API also returns to you some notable features, facial features. So here is a picture of me and my friend Matt. We used to work together back before I was at Google in New York, and he since actually moved to Toronto, so I met up with him the other day. And so we took this picture, and so if I go ahead and press call, I want to try to get this right so that you can see me press call and then watch the red box that I'm going to draw show up in real time. So you can just see how fast local processing looks like. So here we go. There it is. So it's pretty quick. Right? It just, bam. And you can see there, these circles, actually here, let me just switch back to the deck because I do have a screenshot of that. Okay. So these circles, I just literally just said, all right, make a painter draw circles on the pixels that are being returned to me in the API. So there's your eyes, base of your nose, cheeks, edge of the mouth. So you could see, you could add, I don't know, sunglasses or a mustache on someone's face pretty easily. And the API also returns a likelihood of someone smiling between 0 and 1, and the likelihood of someone's eyes being open versus closed, another 0 to 1 scale. So you can do some interesting local things with that. And it also, because of its fairly real-time nature, you can stream that data in. So you could, for example, have just the camera going and overlay anything you feel like, and just have that live and tracking someone's face in that shot. And that's one of the demos that are also available that Google has put out. So that's pretty much the Mobile Vision API. It does faces, barcodes, text, all in similar manners, all local, all no cloud, used. So now let's move on to a different quadrant. This is the Cloud Vision API. You can probably guess which quadrant this is going to go in. It's definitely going to go on the cloud side, and lucky for us, it's actually going to be on the pre-trained level as well, which means it is ready to go. But that also means, double-edged sword, it cannot be trained. You can't give it custom data, right? Similar to the Android Mobile Vision API. It recognizes faces. It does not recognize PVC pipes. Fair warning, right? And so let's talk about that a little bit. The Vision API, just like the Mobile Vision API, is broken down into a number of areas. It will recognize somewhat more things and with somewhat greater accuracy than the local, Mobile Vision API. Of course, you pay for that in network time and network traffic. But you save on computational resources and an expanded plethora of features. Of course, not every app needs every feature. So think about what it is that you're looking for. So the first thing it does is it labels. It labels what's in the picture. In general, it returns a list of ranked confidences with what those labels are. So it might say, audience or talk or academic seminar. I've seen that come back. The second thing it'll do is landmark detection. So you see the picture of the Eiffel Tower there. It'll say, this is the Eiffel Tower. You have taken a picture of it. Good job, you and every other tourist. No. So then it returns also latitude and longitude of that location. So it really knows where it is, and it's not taking the geolocation from the picture. And thirdly, it does logo detection. So logos in the pictures, I'll be honest, this piece is an improving, let's say, feature. It's gotten better. When it first came out, I couldn't get it to recognize the Google logo. So, But nowadays, I've taken pictures in the wild, banners on cloth tables in awkward lighting, and it'll still pick it up. And then face detection. Again, similar to the Mobile Vision API, right? You get where the face is. You get somewhat more features. And you get some other things. You also get emotion back. Rather than just mouth and eye openingness, you get the actual emotion. So the likelihood of joy, anger, sadness, surprise. There's also a headwear likelihood, which is random. And then there's text, OCR, again. So the OCR is something that is available on both, right? It's on the Android local side as well as the Cloud Vision API. So you can play with both, see which set of accuracies you prefer, maybe use one as a fallback in case the network's not available, things like that. And then Safe Search. Safe Search will give you back whether the likelihood of an image being adult, violent, medically related, or a spoof. So you can have fun on Meme Gen with pictures on that, right, on Jiffy or something. So let's see what that looks like. Basically, it comes back as a JSON object, right? Because it's a web call. You can call it not just from Android, but from any platform of your choice. Anything that can make a REST API request, you can use the Cloud Vision API, right? So that means literally anything you have that can hit the web and upload a picture can now do image detection with zero training. I think that's pretty awesome in terms of just giving you that capability with minimal work. So label detection is exactly what it sounds like, right? You guys, at this point, I think have seen most of this slide. It gives a ranked ordering of scores of how likely it thinks each one is, and it's always in descending order. And you request it with a setting of how many you want to see at the most. So in this case, we might have said max 4. But you could say max 40 and get a whole bunch back, but those scores are going to be diminishing. Here's landmark detection. This is a picture of the Universal Studios Wizarding World of Harry Potter. And here, again, latitude, longitude, we kind of talked about that. And let's see, yeah. So then there's this MID, which some of you guys might be wondering, what is this mid? And it's an ID into the Google Knowledge Graph, and that's a read-only API where you literally just stick that key into the upper, not the upper right, but into the URL. Like, it doesn't get simpler than that. And it returns things like a Wikipedia link, some text of the article, and then, of course, you could follow that Wikipedia link programmatically, scrape that. And so you begin to have an opportunity to really get deep meaning out of your pictures. You can go from there, and if there's text, you could OCR it and take that text and keep running with it. This is an example of face detection, and I do want to point out that in this particular photo, I also ran it through logo detection at some point, and it did pick up that Deer Park water, even though it has that lighting and it's in the real-world scenario. So a little plug for the logo detection part of the API. So it comes back with a couple more things like we talked about. One of the things I didn't mention is it comes back with roll, pan, and tilt angle, which means like if the camera is dead center in front of me, that's 0, 0, 0, right? And then this way, and what's the last direction? I'm not a photography expert. This way? Yeah, maybe. Someone was telling me that for me. Thank you. So joy, likelihood, and you see there's sorrow and anger, likelihood, things like that. And then these positions, right? These are some really intense positions here. And in terms of the specificity of them, there's things like, was it the left and right gnathion or something? It's apparently some medical term for chin. I don't know why we couldn't just use chin. So naturally, I have put this into our lovely, really not fancy app. You see we're still here. We're going to go ahead and pick another picture. Well, actually, before we do that, let me just use this picture, right? So we can really do a side-by-side comparison. So I'm going to select the Cloud Vision API, and we're going to call, oh, you guys get to see the time again. So it's going to upload the picture first, and you can see that I put a little text here. It says uploading, and waiting, and waiting, and waiting, and waiting. Okay, I thought the Wi-Fi was broken for a second there. I didn't draw anything on the picture for this one, but you can see the text that comes back is backwards, so I'm going to go to the screenshots and let you guys, we're going to come back to that. All right, so, yep, that looks just like mine. That's good. Apparently, Matt is not smiling as intensely as I am, and so there you got a likely and a very unlikely. And so here, I asked for label, logo, and face. I didn't ask for the other pieces. So when you make a request, you can choose which pieces of the API you're looking for. And the label that the Cloud Vision came back with was like interaction. So sometimes the labels are not as useful, right? Because there's no one thing kind of going on here. Maybe it should come back with selfie or something. And so that actually touches upon an interesting piece of the Cloud Vision API. And all real like online back-ended systems for machine learning is that they can improve over time, right? Perhaps next week, when I send this exact same picture up, it will come back with selfie. Or maybe it'll come back with, portrait with a friend. No. It can change. It will improve over time, and you get that for free, basically. And so when you compare kind of deployment strategy between something that's local on a device, custom or otherwise, right, versus something in the cloud, that's another kind of trade-off to consider. So, see, oh yeah, and this is another example with the wheel that we saw earlier. It comes back with a little more interesting things. So I asked for, I think 10 or something, up to 10 labels. So you would come back with a ton of things. The first thing is spoke, alloy, wheel, family car, wheel. It just keeps on going. There's a lot of terms, and it's not going to, it's no magic bullet, right? It's not a perfect description that, if you ask someone on the street, what is this a picture of? And they might just say, oh, it's a wheel or a tire. I don't know, which one? Is it a wheel or a tire? And of course, no logos, no faces. So I thought it would be fun if we did a little live version. So let's, all right, we're going to do an experiment here. Normally I would ask the lights come up, but they're already up. So I'm going to go to the camera mode. Oh, this isn't showing. So here's, wow, this is really, Inception-y. OK, so if everybody could extend one arm and in front of you and make a fist. Okay, and now raise your thumb up and line that up with your nose. Like put that in so that it comes up with the camera, all right? So if I'm going to get this picture here. I don't have a wide-angle lens, unfortunately. All right, you guys can put your hands down now. It's great. So we're going to send that through and see what it thinks. So let's see here. We got this little piece, and the request from before is still there. So I'm going to hit call. It's going to upload this fresh picture. And uploading, and uploading. And of course, this is backwards, so. Well, there's a lot of things, but unless you're really good at reading backwards text, you probably can't read it. So I'll read it for you here. We got 0.82 crowd. Three is a crowd, but I suppose a couple hundred is a crowd as well. We got audience, youth, convention, academic conference, lecture, and meeting. And that goes all, at meeting we're at like 0.51. And so that's getting pretty low. And it found at least one face with very likely joy. So thank you for that. So let's click back through these. OK, quick plug for the other APIs, just because they're so similar, and I would be, I suppose, remiss to not mention them. So just like the Vision API turns an image into JSON in a meaning, there's also a speech API, same exact concept. It's a web call. It turns audio into text. In a lot of ways, that's simpler than a picture, right? Because you can't really define what is in the picture as easily as you can just take audio and turn it into text. And similar to the Vision API, you can ask for alternatives. You can say, I want you to give me 5 alternatives, and it'll do that. Another thing that it recently introduced, which I thought was a pretty nice touch, is a tiny, tiny bit of customization. You can give it a context phrase. It's actually an array, so you can get a list of context phrases. And you can add things like AndroidTO as like one word, and then you can say it to them, and then it won't put it as like Android, T-E-E-O-H, right? It'll spell it correctly and do the capitalizations. And then if you don't leave it in there, it'll be all weird. So that's pretty nice. And then lastly, the natural language API. Similar idea to the previous two. This time you pass in text, perhaps the text you got from the speech API or the text you got from the Vision API, right? We're chaining machine learning now. And it has 3 methods. One is entities. It'll pull out salient entities from a sentence and give you some information about it, such as that MID, right? And a link to Wikipedia. Sentiment, just per sentence, positive or negative, so that's polarity, and then how strong, magnitude. And then syntax, it'll do the classic sentence diagramming, natural language processing thing we did in grade school, where it's like, here's a verb, it's got this subject and this object, and it's described by that adjective, and all those relationships, so you can build out a nice sentence diagram. Free tiers. Free tiers. For all 3 are available, and it's pretty generous, especially if you want to just play around with it, whether it's calling it from Android, calling it from your Raspberry Pi, whatever thing that can hit the web, right? The 1,000 requests a month for Vision is per type. So it's 1,000 face detections, 1,000 labels, 1,000 logo detections. So it's really like 6,000. Speech, 60 minutes a month. That's pretty vanilla. And then natural language API has this weird counting system because you're sending characters and they're not counting by request. So you don't have to worry about making a request super large and then taking advantage of every request per se, right? So it's just metered by the number of characters sent. So that's what, 5 million Unicode characters a month? And that's just the free tier, right? That's forever, which is great. All right, so moving on from in our chart, we had Mobile Vision API and the Cloud Vision API. That's our pre-trained stuff, right? Local and cloud. So now we're going to go into the custom realm. And the custom realm is pretty dominated by TensorFlow as far as this presentation is concerned, both for local and cloud. TensorFlow, for those of you who are not familiar, is a free open source machine learning library, as in you can download the source code and compile it from scratch for any system or architecture of your choice. And we published it, Google made it about a year ago. It's coming up on its first birthday. Happy early birthday, TensorFlow. And it's especially useful for deep learning, but it is a general machine learning library. And one of the things that it really is good at is translating research work into a production environment. Whereas in the past, research papers would come out, and then people would go implement it in a totally different language, right? Literally, there were research papers that spent the first X number of pages introducing custom syntax, custom, it's a custom library basically, right? So defining terms, and this is the thing we're gonna use. And then people have to go backwards and then go back and try to implement that once the paper came out. But now you can literally just say, here's a paper, here's my TensorFlow code on GitHub, you can run it. That's it. So it's pretty exciting, and it's seen a lot of adoption very quickly. So how do you get TensorFlow on Android? You put an Android on top of TensorFlow, and now you have an Android on TensorFlow. Maybe, I guess it's TensorFlow on Android, so I should have reversed those images. So let's see. You might be asking yourself at this point, why do I need TensorFlow? Those other APIs that Yufeng just talked about seem great. They do everything I need. I only have image recognition and speech recognition problems in my life. So I'm all set. And if so, feel free to take a nap or something. But if you have any sort of custom work you need or might need done, please stay awake. So TensorFlow, of course, lets you do the custom stuff, right? Because sometimes, they gotta cover this piece, right? Sometimes you have a very particular problem, and you need a very particular set of skills, yes? All right. Like these guys, right? They have a very particular set of skills, and they will solve your problem. If your problem is identifying whether someone's mouth is open in a picture or not, Mobile Vision API is your guy. If you need to identify whether an image is a spoof or not, you're all set. But if you need, like going back to that silly example of the PVC pipe being bent or straight, if that's your problem, then you're out of luck, right? Speech API is not gonna solve your problem. Natural language API is also not gonna solve that problem. And so then you need to look into more customized solutions. So in our little diagram, TensorFlow, of course, as you probably know by now, covers this bottom spectrum. And we're gonna stick an Android up over there. And so that's your local custom version. So let's see that. TensorFlow is capable of generating some pretty large file sizes, right? A machine learning model can be very, very large. And so when they went to make TensorFlow for Android, a lot of the focus was put into how do we cut this down? How do we cut down file size? How do we cut down processing requirements, right? Battery life concerns. And so the result, let's see if, this is going to be interesting because I can't point the camera anywhere but at myself, so the response is going to be, well, perhaps less than stellar. So this is a live example, right? So it moves, right? And it's doing live predictions. So yeah, I mean, it's going to say all sorts of stuff. I think it says notebook right now, which is kind of bonkers. And the custom model that this is running, it's a limited data set. I was looking at the possible answers that it could come back with. It had things like terrier and just all sorts of very specific things like starfish and American lobster. So a lot of the everyday things like a water bottle. Well, actually, I think water bottle might work. Water bottle? Who can read backwards? There we go, water bottle right at the top. And also pop bottle, localized to Toronto perhaps. So let's see, I have some better screenshots. So there's that car wheel again. So this is me using the phone against my computer screen of the screenshot from earlier to get that result because it's a live feed. And then this was a picture of a vending machine, same idea. These happen to work well. It is a little bit cherry-picked, just for this image recognition use case. But the idea here is that TensorFlow can do a lot more than just image recognition. Right? We're looking at the image recognition problem here just to give an equal comparison between the different APIs. But the point of TensorFlow, it's just a computational library. So you can feed it your big data sets and all of that good stuff. And in fact, that's really where you begin to see it really shine. And that's where a lot of the code labs are directed toward, not just the image problems. I think I have one more. Oh yeah, there's the actual computer keyboard. For some reason, it decided to recognize the spacebar. So TensorFlow runs locally on mobile. broadly speaking. And because you have the source code, if you want to compile it from scratch for a different architecture, you can do that. These are officially supported ones with ready-to-go samples that you can just run out of the box. So mobile is great, and it does a lot of local processing. But sometimes you need more horsepower, right, for that prediction step. And this is where we go back to that slide from earlier and thinking about prediction versus training. In the prediction step, it doesn't have as strong of computational requirements, but there are other limitations, right? On mobile, there's size constraints, power constraints, and things like that. So if you need additional power, right, you could add this. I don't know if that looks as good on this, or there's a dot in the middle of that hexagon. But basically, running something in the cloud, right? Running your TensorFlow prediction code in the cloud. So now we're talking basically about deploying kind of your own vision API, but instead it's your like PVC pipe recognizer API to the cloud. So you're running TensorFlow prediction in the cloud, and you're hitting that custom endpoint yourself. And I did not build a custom PVC pipe recognizer. Sorry to build up the suspense on you on that. But that's the idea there, right? You take TensorFlow and you put it that way. Here's an example that someone did build, which is far more interesting than a PVC pipe recognizer. So this farmer in Japan, his mom sorted cucumbers for him, and in the high season. And there was lots of different kinds of cucumbers. They need to be sorted for shape, size, goodness in general, right? How tasty is that cucumber going to be? And he had a little camera, and after he said after kind of seeing TensorFlow's performance in AlphaGo, right, back in the day when, not back in the day, but when he defeated Lisa Dole in the Go, and he's like, hey, let me try this thing, and he found it to be so amenable and so straightforward to get started with. He was able to sort these cucumbers. And there's 9 kinds of cucumbers. I thought there was just 2, European and not. And so this is, because I'm running short on time, I'm just going to let this play and talk over it and not do the audio, because I promised the guys in the back there's no audio. And there's not, because the sound is basically a whirring machine the whole time. And let me move my computer. So there comes the cucumbers, and it just like slaps them out, depending on where they need to go, into these different, you can see kind of the cardboard bins underneath. And that's pretty much how it goes. But it worked for him, right? It did well enough compared to an expert, right? His mom is an expert at recognizing and classifying and categorizing these cucumbers. And this was able to automate what literally he said would take up to 8 hours a day in like kind of the high peak season of sorting cucumbers by hand. So that's really kind of fun, a little fun example. Now, I don't want to take too much time on TensorFlow, because we actually have later in the program a talk and a code lab, both from my colleague Vihan, and he's going to talk about TensorFlow, and you guys can get some hands-on time with it. And so that's pretty much our chart, right? We've filled it out. We have the mobile vision API for Android, which runs locally. It's free. There's no network traffic. It's fast, pretty fast, but it doesn't do everything, right? The barcode does text, does a little bit of face stuff, but you can do a lot more face stuff if you wanted to. And you do that in the cloud. But then you pay for that with latency and 1,000 requests a month. And then on the custom side, right, you have TensorFlow, but you can choose to deploy that locally on mobile, or you can deploy that to the cloud and do training in the cloud. And similarly, you pay for that with latency. But when you go to custom, you can do your own problems. You can sort cucumbers. Instead of just recognizing, yes, that there in the picture is a cucumber, you can say that there is this type of cucumber, right? And so that's introducing that custom training. And so that's kind of your axes, right? What kind of performance characteristics do you want, and what kind of customization level do you want in your model? And so with that, because my time is running short, I'll leave you guys with this slide. Again, you can ask me, feel free to find me on Twitter, ask me questions at ufangg. Basically, the links are pretty straightforward. It's cloud.google.com/whatever API. The Vision API is part of Android, so that's under developers.google.com. And then TensorFlow decided to do its own thing. And so it's at tensorflow.org. There's some great getting started material up there. The quick start does the classic handwritten number recognition problem. It's the MNIST data set, for those of you guys are familiar with that. Basically, you can literally, in probably less than an hour, have running locally on your laptop, a system that recognizes handwritten digits that you can just write, write 9, put the image in, oh, it recognizes a 9, and with like literally over 90% accuracy. So yeah, thank you, and if we have time for questions, otherwise we can just do the transition.